Today we are finishing up lesson 6.3, which is day 2, parametric equations and motion. And to be honest, I really do believe this is one of the more difficult lessons. So if you're experiencing that, just know that is totally normal. You will also see on Math Excel, I believe I only assigned 12 or 13 questions, and I also made it due Wednesday at midnight. I strongly encourage you to get on and do some of it today. And then if you've got questions, we can get on through Zoom and finish them up between Tuesday and Wednesday. Do not wait until the last minute. Okay, the first 3 are just kind of warm-ups of some of the operations that we have done with vectors, and you should have also done the warm-up on Canvas. Again, just trying to help you because we got a quiz coming up at the end of this week as well. So we're looking for find 2u minus 3w. So I'm going to take vector u, I'm going to go ahead and multiply it by 2. And I'm just going to change this to adding a negative. So I'm going to add a scalar of negative 3 times vector w, so that's negative 3 and 9. And finally I add my corresponding components and we get 1, 7. Okay, the next one we've got w minus 2u, and remember these are not absolute value bars. That means we want to find the magnitude. So the first thing we want to do is go ahead and let's do vector w, and again I'm going to just change this to adding and negative 2 times vector u, negative 4 and 2. I'm going to add those vectors together, negative 3, negative 1, and then I'm looking for the magnitude. You do have a formula. It's the square of this plus the square of this, taking the square root. Or if we want to visualize the vector negative 3, negative 1 would be here. The magnitude would be that length. Again, we end up using Pythagorean's theorem. So we've got negative 3 squared, negative 1 squared. We get radical 10. And then finally, we've got the dot product of vector u times vector w, or v. And if you remember, when you're multiplying 2 vectors, we actually end up with a scalar. And the way we find that is we're doing 2 times 4 plus negative 1 times 2 and adding those together, and we get 6. All right, now we start the application. So the first one tells us we have a distress flare that is launched. It gives us the vertical velocity, and we're looking for the height against the time. And if we come down here, we've actually been given the 2 equations. So we've got x is equal to the time. If you remember, this 76 is your initial velocity. And the 75 is your initial height. And that negative 16t squared never changes. So I'm going to go ahead and grab my graphing calculator. You want to make sure you are in degree mode, and you want to make sure you are in parametric mode. And I'm going to go ahead and go to y equals, and I'm going to type in the 2 equations. So x is equal to the time, and then our second equation was the negative 16t squared. Got an extra t in there, plus that initial velocity times time plus the initial height. I'm going to try, unfortunately, remember on these sometimes you don't have a set method for coming up. I'm going to go ahead and try zooming in on, I'm going to try zoom fit, and let's see, and actually it pops up pretty well. Let's go take a look at our window. So it looks like our time is from 0 to 5, and we're going counting by steps of 0.5. Our x is going the same thing. Our x scale is going by 50s. Let's go ahead and change that. Let's just go change that to 1. I'm going to change this to 1, maybe 180 and 10. And again, we should see, I'm still not seeing quite the entire graph. So let's go back and change that one more time. let's go to, we need to go to a larger y max. So let's go to maybe 10. And now it looks like we've got a better view. Go change this to -10 just to make sure. I don't like that either. So let's go here. Okay. So a couple questions they want us to figure out. They want us to figure out what the time is, or given each of the different times, what is that corresponding height. So two ways we can do this. We could go ahead and plug in a time of 1 into each of these locations. Let's go ahead and do that to begin with. -16 times 1 squared plus 76 times 1 plus 75. And we end up with 135, and that would be feet. The second way is we could go and look at our table. Let me zoom back out. Actually, let's leave it since we're zoomed in on that. So I'm going to go into my table, and I want to make sure it's on. I can either do auto or ask. Let's just leave it on auto. When I go into that table, I can now see when it's 2 seconds, it's 2 for my x and a height of 163. And then it asks me for 4 seconds, which again is here, 123, and it asks me for 5 seconds, which is 55. So again, you can use your table that way. If we wanted to do ask it, we could go down to ask, going back in there, and I could type in the time of 2 seconds. I think the next one was 4, and the next one was 5, and again, it's generating all of those corresponding heights. So let's go ahead and write those down. So at a time of 2 seconds, we were at 163 feet. At a time of 4 seconds, we were at 123 feet, and then at a time of 5 seconds, we were at 55 feet. Okay, let's move on to the next application. It says that Kevin is throwing a baseball 3 feet above the ground with an initial speed of 150. And again, remember that speed is the same thing as our velocity, and we've been given an angle. And it wants to know, will the ball clear a 20-foot wall that is 400 feet away? So we've got our two general equations, and again, you should see these on your formula sheet. We've got x equals our initial velocity, which is that 150 cosine of 18 degrees times the time. We've got y equals -16t squared. Again, looks like I left off a 0. 150 sine of 18 degrees times the time, and our initial height was 3. Okay, I'm going to pause it to give you a moment to go ahead and enter those equations on your graphing calculator. Okay, I typed in my equations. I hit zoom fit. When I went to graph, I'm coming up with this graph, which isn't that great, but at least I can see it. I'm going to go into my window. I'm going to go from t is my time. I can't believe it's 360 seconds, so maybe we'll count by tens. We can go by 0.5. 0, I know that the wall is 400 feet away, so I'm going to just type in 425, maybe count by 20s. I've got 0 and maybe a height of, I don't know, let's take 200 and again count by 10s. Okay, let's see if we don't get a better picture of our graph there. A little bit better. It looks like I maybe want a little bit more here, and I don't need quite so many y values. So I'm going to go change that y value to maybe even just 50. Let's count by 2s. And let's go a little bit more out on our x's. Okay, a little bit better. So the question is, when this ball is thrown, will it be clear a 20-foot wall that is 400 feet away? Well, we could try using the trace button. Now notice when it's counting by 2.5 seconds. So I could go and change that step if I wanted. So I'm going to count maybe by 0.25 seconds, so maybe that will give me a little bit better. Now when I trace, so let's see, the wall is 400 feet away, which I'm a little bit over, so it's still tough to tell because at 2.75 seconds, we're at 392 and only 9 feet. So really it looks as though it's a no because the height of that wall has to be is 20 feet. Now, the irritating part is I'm kind of locked into this graphing calculator. So here's where I'm going to show you another option. Okay, so here's the rough object that's being thrown, and I know that I've got a wall somewhere over here that is 400 feet away. I'm just not sure if it's before or after where that ball lands, but I know I want to be at 400, and that's my x distance. So what I'm going to do is I'm going to set x equal to 400. We've got 150 cosine of 18 degrees times the time. I'm going to solve for the time. So I'm going to take 400 and I'm going to divide by 150 cosine of 18. The only other thing, I'm going to put that in parentheses just to be safe. And we end up with a time of 2.803899. So at that time, I'm 400 feet out. I need to know what my vertical distance is. So if I go back into my table, I can do an ask. It's on ask. And I'm going to type in what that value was right there. Now remember, I can either type it in or I've got that stored in my answer. So I'm going to hit second answer. It pulls up that time and it tells me at that time I'm 400 feet out, but I'm only 7 feet above the ground, which is roughly what we got when we looked at our graph. So again, in either case, algebraically or graphically, we can see that our answer is no. And I'm just going to put at a time of 2.8038. I was at 400 feet for my horizontal distance, but I was only 7.1783 for my vertical distance. So my answer would be no. Okay, let's go on and look at another example. Okay, and this one is really similar to that last one. I just wasn't given what those equations were. But again, it said our x value is equal to the velocity cosine of your theta times time. Y is equal to -16 t squared plus our initial velocity times the sine of theta times time plus our initial height. So let me give you a minute to read through it and write down what those equations would be. Okay, for the second one then, again, I went ahead and wrote out my equations. I went ahead and typed them under y equals, and then I played around with my window, and this was finally the window that I got here. They want to know after 0.5 seconds how far has the javelin traveled horizontally and vertically. So two ways I can do this. Again, I can hit trace, and I want to know 0.5 seconds, and I just set that I was counting by 0.25, so I just go to 0.5 and I can see my horizontal distance is 22.98. My vertical distance is 23.98097. My second option, again, I could go into that table. I could type in a 0.5, and again, it tells me what each of those values are. Okay, so I went ahead and wrote down my time, my horizontal, my vertical. I'm going to try and show you maybe two more things with respect to this graph. Let's suppose it wanted to know at what time am I going to actually hit the ground, and what is that vertical distance. That means my time is 0, which I would plug in 0 here for y. So in other words, I actually have a quadratic, so I'm going to go ahead and run that program. my quad, I've got